Welcome back, learners. Welcome back to the Govan Mbeki Mathematics Development Centre YouTube channel. In this video on CAPS Mathematics Grade 12, the topic is Euclidean geometry, and this is the second part of the two-part video series on Grade 12 Euclidean geometry. Part 2 being the similarity theorem and converse theorem, and concepts and applications related to this these two theorems. Hi, welcome back to Maths with Armin. This video on Euclidean geometry, it's part 2 of 2. In part 1 we had the proportionality theorem. In this part we looking at the similarity theorem and approach to problems relating to the similarity theorem. Hope you will enjoy the video. This lesson consists of 5 units. The first one there, we're going to look at the similarity theorem and its converse and all the concepts relating to the similarity theorem. Then we're going to look at the different types of assessments on using the similarity theorem. Then there are two types of applications. The first one I refer to as direct. We're going to look at some problems that are direct applications, and then we also have problems that I refer to as indirect applications. And then, as usual with all the videos, there's always a exercise worksheet. Hope you will enjoy the lesson. In this unit, we're going to look at the similarity theorem as well as the converse of the similarity theorem and concepts relating to these two theorems. Now, before we actually going to start with the formal proof of the similarity theorem, let's just look at the statement of the theorem and try to understand the statement. So let's see there. If two triangles, so we first of all need two triangles. Here's a triangle ABC, and there's another triangle DEF. These two triangles need to be equiangular. What we mean by equiangular? For example, this means that angle A will be equal to angle D, okay? And angle B will be equal to angle E, and angle C equal to angle F, right? That is what we mean by equiangular, right? That the angles of the one triangle is exactly the same size as the angles in the other triangle. Now, then, once we have that, then their corresponding sides, there the triangle's corresponding sides are in proportion. Now what do we mean by that? Corresponding sides, so if I take AB, right, you see AB is a side and AB is opposite angle C, but C is exactly the same as angle F, and the opposite side there will be DE. So AB and DE correspond. Okay. Similarly, if I take BC, you can see BC is opposite angle A, and angle A is the same as angle D, and the side opposite D is EF. That's why it's BC over EF. And then we have the last one, AC, which is opposite angle B, but angle B is equal to angle E, and the one opposite angle E is DF. And that is what we mean by because I can have AB is to DE is equal to BC is to EF is equal to AC is equal to DF, and they form a proportion. If you have a ratio equal to another ratio, that forms a proportion. So if the two triangles are equiangular, then their corresponding sides, important to be able to match the corresponding sides, are in proportion. Now, if two triangles are equiangular, we also can refer to them as being the triangles are similar to each other. And this is the symbol notation that we use to indicate that two triangles are similar. Now, what's important, the order in which the triangle is labeled is important, because if it's stated ABC is similar to DEF, it means A must match with D. angle B is the same as angle size as angle E, and angle C is equal to F. I cannot just write it in any order, right? Because if I have it in this order here, it's possible to get the proportion without even looking at the diagram. Let's see how we can do that. And this is how we go about it. We take the first two letters AB over the first two letters DE, right? And there I have AB over DE, or AB is to DE. Then I take the last two letters, which is BC, over the last two letters EF. So BC is to EF, and then I can take the first and the last letter over the first and the last letter. And that is how we can get the proportion. Right, let's go over that again. You take the first two letters over the first two, and the last two over the last two, and the first and the last over the first and the last, right? So if two triangles are equiangular or they are similar, that implies their corresponding sides are in proportion. Now in the next slide, we're going to actually prove this theorem to you formally. Now we're actually going to formally prove the similarity theorem. To be able to do that, we're going to label two triangles. So in triangle DEF and triangle ABC. Note the colors that we're using for them. Is given that angle A matches with angle D, and angle B matches with angle E, and angle C matches with angle F. In other words, the two triangles are equiangular. Now we have to prove the theorem which states that, what does it state? That their corresponding sides are in proportion. Note that the proof of this theorem is examinable, so it's important that you do understand it, and that you can, if this question is asked, you won't have any problem in responding to it correctly. Now we want to start with the proof, but to be able to prove this, we need something to assist us. And this we refer to as our construction. It's things that we add to the given information. So the first thing there is we need to draw MN. See, there's MN on the triangle DEF, such that AB is equal, AB you can see is equal to DM, and AC equal to DN, right? So in other words, we draw it so that AB is exactly the same as DM, and that AC is the same as DN. Now, if we look at those two triangles now, we notice triangle ABC and DMN, very easy, they are congruent. And the reason why they're congruent, I've got a side and an angle and a side. Side, angle, side. So the first thing there, I notice those triangles are congruent. Now, if triangles are congruent, there should be more parts of the triangle that will match. That's correct. We'll have angle B will now match with angle M1. So B is exactly the same as M1. Let's mark it off that way as well. And we also know that the sides, corresponding sides, will be equal. MN will be equal, says MN is equal to BC, right? Also, the third angle, this angle N1 will be equal to angle C, but let's leave that one out. Now, if we look at our M1 and E, we now see that they are equal. M1 is equal to, from our deduction that we made from our congruency. And what type of angles do they form? That's correct. They form corresponding angles. And if corresponding angles are equal, then we get parallel lines. Therefore, MN is parallel to DF because we have equal corresponding angles. Now, what does this remind us? A line parallel to one side of a triangle, that's correct. It divides the other sides in proportion. So that's our proportion theorem. So let's apply the proportion theorem. dm over de equal to mn over ef and dn over df. But if we look at that, dm was part of my construction, but dm is exactly the same as AB, so we can replace dm by AB. Mn is exactly the same as BC, that's from our congruency. And dn is equal to AC, that is from my construction. And if we do that, So if we use our construction and our congruency, we end up with that statement. And there we've proved if two triangles are equiangular, then their corresponding sides are in proportion. Exactly the same that we have there. Now let's look at the converse of the similarity theorem. Let's look at this statement here. Triangle ABC and triangle DEF are given such that their corresponding sides are in proportion. Now if their corresponding sides are in proportion, then in other words I have AB over DE, I have BC over EF, and I have AC over DF. So we are given the corresponding sides are in proportion. That's just what is given, right? AB over DE is the same as BC over EF, is the same as AC over DF. Now if we have that, that would imply that the two triangles are equiangular. Okay? In other words, triangle ABC will then be similar to triangle DEF. Let's look at the formal statement of the converse theorem. If corresponding sides of two triangles are proportional, in other words, we have this, then the two triangles are equiangular. Note that we're not going to do the formal proof of this converse because the proof is not examinable, but it's important for you to understand that if the corresponding sides are in proportion, then the two triangles are similar or they're equiangular, or the other way around. If they are equiangular, then the corresponding sides are proportion. So that's the converse statement thing. Now it's important that you need to know the interrelationship between the following three concepts there. Equiangular, that means all the angles of the one triangle is exactly the same as the angles of the other triangle. Now if they're equiangular, we actually refer to that as the triangles are similar. So if they are equiangular, it means they are similar. If they are similar, it means they are equiangular. The one implies the other. And if they are equiangular, we just proved as well that their sides are in proportion, right? So they're equiangular, they mean they're similar. If they're similar, they are in proportion. And if they are in proportion, we just proved we just looked at the converse, then they must be equiangular. So always keep these three things in mind: equiangular, similarity, and proportion. They always go together, right? If it's equiangular, there'll be proportion. If it's proportion, they'll be similar. So if we want to prove a proportion, we just show that they're equiangular, or we show they're similar, right? If we know they're similar, we can then deduce the sides are in proportion, right? Or if we know they are equiangular, then their sides will be in proportion as well. In this unit, we're going to look at all the different types of assessment possible relating to applications of the similarity and the converse of the similarity theorem. Now, I identify two types of applications. The one is a direct. In other words, the question clearly states, prove triangle 1 is similar to triangle 2. Right? So it clearly states that you want to prove the triangles are similar. Right? No doubt what your objective is here. Prove they are similar. Then we get another type of question here where the similarity notation is not used in the question, but you actually have to prove that they are similar. And questions are like the following. When we have AB over BC equal to DEF or EF, when you have a proportion like that, they're actually asking you indirectly prove that they are similar. Because once they're similar, you can then get the proportion. Okay, so in other words, you have to know that you have to prove that these two triangles are similar first. Once they're similar, then you can get that. Let's look at the next one. Here we just have the proportion written in a different way, right? I've just taken maybe the BC on the other side. So there's another type that looks like that. Okay. And then we have a third type where we actually have a product involved, not a quotient there. Right? And then we have another one where we have AB squared. Maybe I could have had AB with another AB here, and AB times AB is AB squared. So they all basically mean that prove two triangles are similar. Prove two triangles are similar. prove two triangles are similar. Prove two triangles, because once they're similar, you can get the proportion. This is just another way in which the proportion statement has been written there. And when we have another one here, which involves squares and adding together, right? So you've got AB squared equal to BD squared plus, so there's a sum of squares here. And the sum of squares, this should remind you of a particular theorem here. That's correct. Maybe this is the theorem problem here. We're going to use most probably the theorem of Pythagoras. And I've indicated this is a level 4. This one is a little bit more challenging than the others there, right? So indirectly, you must first prove them similar, and once you get similar, you can get to that. First prove two triangles similar, and from the similarity you can get the proportion, and you can write it in that form. First prove two triangles similar, you can get the proportion, and you can just cross multiply, right? Same way here. First prove two triangles similar, you can get the proportion, and when you cross multiply, you might end up with AB squared. Here we're going to most probably apply the theorem of Pythagoras. And that's what I refer to as a direct application. And indirect is easy. They just tell you exactly, prove that angle A is equal to angle D, prove that angle B is equal to angle E, and then angle C is equal to F. That's very direct, what you have to do here. Here it's indirect. You first of all have to determine which two triangles are similar. Which two, right? Because they are not given in the order there. And I'll show you a technique how you can easily get the order of the two triangles correct. Now let's look at the direct type of application here. This question here, prove two triangles are similar. Now remember we said similarity has to do with equiangular, and similarity has to do with the corresponding sides being proportional. Remember there are three. So similar, what is the other two? So in other words, we can first prove that the corresponding sides are in proportion. If we can't do that, we can then prove that the triangles are equiangular. It depends on the given information there. You can see there, similarity goes with proportion, proportion goes with equiangular, right? So it just seemed to go around like we had in the I showed you previously. These three things always go to the right. So if you must prove a direct application, you either look at the corresponding sides if you have side lengths. If you don't have side lengths, let's determine whether the two triangles are equiangular. Now let's look at some direct applications requiring the similarity theorem. Now let's look at our first example here. In the day we have two diagrams, triangle ABC with some measurements given, and triangle DEF with some measurements given. And we have to prove that they are similar. So here, this is an example where they give us lengths. So you can see what are we going to do? We're going to see whether the corresponding sides are in proportion. And what do we have to do? Get a ratio and another ratio and another ratio and see whether they are equal to each other. Now, you might know how to do this, so we give you a chance. You can pause the video, do the solution on your own, and once you've done that, you can go to the next slide. Consider the approach that we're going to use there. There we have two triangles, and we've got the lengths of the sides are given. No angle measurements are given. And we want to prove that these two triangles are similar. So first thing that we want to do is just create a template. Remember, we want to set up a proportion. So just have a template like that. So you can just have equal. You're going to have a numerator and a denominator, numerator and a denominator, numerator and a denominator there. Okay. Now what you need to do here is you have to arrange the lengths, the side lengths in ascending order. So take the one triangle, arrange the three sides from the smallest to the largest. So that is 8, 10 and 15. And the other one 24, 30 and 45, right? So we're going to take the three sides in ascending order and we will populate our template that way. So let's see, 8, then 10 and then 15. We look at the other side in ascending order. That is 24, and then it's 30, and then it's 45, right? So we just populate our template with the links, but do them in ascending order, or if you like, descending order, as long as you're consistent. Numerator in ascending, denominator in ascending there. Now we need to label those links there. 8 is the AC, right? So 8 will be with the AC, right? And the 24 goes with the FD. So we take each of those fractions and we just label them. AC goes with 8, FD is the 24. The 10 is the CB, and the 30 is the FE. The 15 is the AB, and the 45 is the DE. Now we can simplify each of these fractions, and if we simplify that, we end up with AC over FD is 1 over 3, CB over FE is 1 over 3, AB over DE is 1 over 3. So they're all equal to each other. Therefore, we get a proportion. I can say AC is to FD, so this is ratios that are equal, so I get a proportion. Now, we want to try to get the triangle in the correct order, right? Let's see how we can do that. This is triangle ACB. So can you see that in the numerator I only have an A and a C and a B. Those are the only letters I have. So if I have AC, the third letter of the triangle must be B. If I have CB, the third letter must be A. If I have AB, the third letter is ABC, ACB, CBA. So AC will become the B, CB will become the A, and AB will become the C. So let's see, that's actually what we're doing now. Because opposite AC I get the B, opposite CB I get the A, opposite AB I get my C. And in exactly the same way, opposite FD, because it's FDE, opposite FD is the E. You can see there's FDE, FED, DEF. You just make up the triangle there. So angle B matches with angle E, angle A matches with angle D, and C, F. So we've got them in the correct order there. And there we've proved that the two triangles are. Now here's an example for you to try on your own. There we have a diagram with some measurements in there. I want you to read that on your own first. And we have to prove AMS is similar to TCS. And then there's a calculation where we have to just substitute some lengths and work out a missing length there, right? So let's pause the video and you try it. And once you've done that, you can go to the start again and we look at the next slide. Now let's look at the solution of this problem there. There we have our diagram with all our information. And we're required to prove that triangle AMS is similar to triangle TCS. And you can see here we've got side lengths, not angle measurements. So we're going to use the approach to see whether the corresponding sides are in proportion. To do that, we need to remember we said from the shortest to the largest. So it's 16, then 30, and then 14, corresponding with 4 and 7,5 and 8,5. So let's start MA with TC. Let's do that. AM over TC is 16 over 4, and that is 4. Then we take the next length, AS with ST, and that is 30 over 7,5. We simplify, it gives us a 4. And the same way, MS with SC, and that gives us also a 4. We notice that those fractions are equal, therefore the corresponding sides are in proportion. Now, if they are in proportion, that means they have to be similar. Now, how can we get that without looking up there? The triangle is AMS. So opposite AM is a S. Opposite AS is a M. Opposite MS is the angle A. The same way there, I have TCS. So opposite TC is angle S. Opposite ST is angle C. Opposite SC is angle T. And there we have our triangles where the angles are in the correct order there. We can just double check. S goes with S. That's exactly what they wanted. S with S. M with angle C. M goes with C, and A goes with T. Right? So there we've got them in the correct order there. Let's look at the second question. We want to calculate the length of BT. Let's look at our diagram. BT is part of BC. Right? And they tell us that triangle AMS, this triangle up here, is similar to the larger one. So this is given. We don't need to prove that. If two triangles are similar, then the corresponding sides are in proportion. So what will the corresponding sides be? AM over AC, MS over CB, AS over AB. That's exactly what we have here. And now we want to calculate, let's see what we have. AM, we've got AM's measurement. AC, we've got AC's measurement. MS, so we've got, and CB is just BT plus 4. So there's only one. I can use the first pair there. And substituting, let's just see whether our substitution is correct. AM is 16, AC is 38,5, MS is the given 34, CB is the BT plus 4. How can we simplify that? We just cross multiply, and then we can solve for B. Let's see how we can get B. So that's 34 times 38,5, subtract 64, everything divided by 16. And if we calculate that, that is 77,812.5. Let's look at another direct type of application here. In this case, we're going to prove similarity making use of equiangular. This basically requires 4 steps, and I'm going to show you what we mean by the 4 steps. First of all, we need to identify the first pair of angles. Secondly, we need to identify the second pair of angles that are equal. And then thirdly, we can identify the third pair of angles that are equal. And then we can make our conclusion by writing the triangles in the correct order. Right? Now, it might be necessary, if you want to find the second pair, that might require more than one step to be able to get that second pair. And this I will refer to as a multi-step reasoning there. And this will illustrate to you in some examples. Let's consider an example now where we're going to prove that two triangles are similar making use of equiangular. Let's look at this situation here. A boy, right, he wants to estimate the height of this traffic light pole. He wants to estimate how high is that pole, right? Now, to be able to do that, he's not able to actually measure the pole. It's very high, I won't be able to measure it there, but he's going to make use of some mathematics and trigonometry to help him here. He moves away from the pole. He moves 5 meters away from the pole, and he places a mirror on level ground, right? And he wants, now, if he stands at the mirror now, he can't, the reflection of the top of the pole is not in the mirror. So he moves away from the mirror gradually, and he focuses on the mirror until he sees the top of the pole reflected in the mirror. Okay, and then he stops there. Right? So now we'll be able to determine the height of the mirror using the measurements there. He knows the measurement PM, that was 5 meters. He can measure the distance that he walked away from the mirror. That's not difficult to measure, and he knows his height. Right? So let's look at the solution of this in the next slide. Let's look at the solution. There we have our diagram, and we have to prove that triangle ABM is similar to triangle TPM. Okay. So how do we start? First of all, we have to identify the first pair of angles. Now, to be able to do that, just look at the labeling of the two triangles. ABM, TPM. We can see the letter M occurs in both, and it's exactly in the same, it's in the last position. So that is an indication that we need to start with angle M. Okay, so let's look at angle M, and we were given that M1 was equal to M2. Therefore, M1 is equal to M2, that is given. Now we need to identify a second pair of angles, and if we can look at our given information, That's correct. We see angle B is equal to angle P, and why are they equal? They're both heights. It was actually given as well. That was a vertical pole, and the boy was standing up straight. Now I need to identify our third angle, and our third angle there would be angle A. There's a third angle A and angle T. And the reason for that is sum of the angles of a triangle. Now in the third step, you can always give your reason for the third step as sum of the angles of a triangle. Because if you already prove that two angles of the triangles are equal, then the third one must be also equal to each other. Okay. And now we can make a conclusion. And our conclusion there is, you see, we took MBA, so there's MBA and MPT, right? Or we can just write it down as what the question stated, ABM similar to TP. And let's just follow M with M, that's correct, M is with M. B with P, and B is with P. And A with T, and we've got A with T. So there we've proved that those two triangles are similar. Now let's look at the second question of this example. We want to find the height TP. Remember, that was his objective. We want to find the height of the traffic light pole. Okay. So we just proved that the two triangles were similar, right? Now if they're similar, then their corresponding sides are in proportion. So let's get there's ABM. So what can we get there? AB over TP, BM over MPM, AM over TM. So there's our proportion there. But we don't want to use all three of them. We only need a pair. Okay? And we need to identify the pair that we're going to use. AB, so we definitely have AB. TP, that's missing, so I definitely need to use AB and TP. BM, we have BM's measurement and we have PM's measurement, so we're going to use the first pair there. Now if we substitute, then we see we get 165 over TP, 130 over 500. We could calculate TP, which is 500 times 165 divided by 130. And if we calculate that, approximately it's 634,62 centimeters, a little bit more than 6 meters high. Now here's an example for you to try. Let's look at this here. We've got a circle ABCD. There's a circle ABCD. Those are points on the circumference of the circle. And AC and DB. There's AC and DB. They intersect at E. Right? And we've labeled E1 and E2 there. We must prove that these two triangles are similar. And then we have to calculate the length of EC based on the given measurements there. Now let's look at the solutions. We must prove that those two triangles are similar, ABE and DCE, right? So we know we have to give reasons why A is equal to D and why B is equal to C and why E is equal to E, right? A little bit of advice, look at the labeling of the triangle, right? Because the labeling can give you an indication which would be the easiest angle to start with. What do you notice there? That's correct. We notice that the first pair of angles we can start off with E, because we have a E, there's a E and a E. So let's start with the E. What do we know about the E's? That's our first pair of angles. It's E1 and E2. And why are those two angles equal? Why are they equal? Because they are vertically opposite, right? Now we need to get a second pair of angles. Do you see a second pair? That's correct from our circle theorems there. Angle A equal to angle D. Angles in the same segment, right? Now you have more than enough. We can just see what is the third angle. We can just write down the third angle. And the third pair there would be angle B and angle C. And you can always write down the reason as sum of the angles of a triangle. Now we can get the triangles in the correct order. So it was E, A and B, and E, D and C. Let's just check that. E, A, and B. E goes with E, A goes with D, and B goes with C. Make sure that your order is correct. We can just verify here. E with E, yes, that's E, must be with E. A with D, let's check. A is with D. And B with C, B is with C. The order is correct there. Right. And then you just write in here, angle, angle, angle. Now let's look at the second part of the question where we're going to actually apply our similarity here. So there we have our diagram again, and we just inserted the measurements that were given. EB is 10 and AB is 12 centimeters and DC is 7,2. Okay. Now we want to calculate the length of EC. So we just proved the proportion, so we need to use, we just proved the similarity. We just proved the similarity. So from the similar triangles, we can write down the proportion, right? And remember how we did this? The first two over the first two, the last two over the last two. So let's do that. AB over DC, BE, right? Because the triangles are similar. So whenever you have the triangle similar, you should be able to get the sides in proportion, right? The corresponding sides in proportion. Now we don't use all three of them. We need to see which one is it. Let's check. AB, I've got AB, so I will use AB. DC, I've got DC's measurement BE, so I'll use the first two, right? I don't have AE and I don't have DE, so I'm not going to use that one. So let's just select those two and then we substitute. So this is the pair that we're going to use because there's the CE we want and we have the other three measurements. So let's substitute the measurements, and there we substituted them. After substituting, we can cross multiply, and then it's easy to work out CE. Don't even need a calculator. With this example, it is 6 centimeters. And there we calculate the length of EC, right? Let's just briefly go over that. You know, if in your previous question you proved triangles similar, they will not ask you to prove it similar if you cannot use it. And how do you use it? By getting the corresponding sides in proportion. Then you write down the, so from this automatically do this, and then you just have to see which pair you're going to take, right, based on the question and based on the given lengths and or measurements that are provided. Now here's an example for you to try, another direct application. It's always important to read your information. You've got BD is a tangent. Okay, so it may be advisable to highlight, to remind you that BD is a tangent of a circle. So you know, if they mention it's a tangent, you need to use it. So you need to use the tangent chord theorem there. Right. So always make sure that you read. You've got a circle. This is the ACD is a straight line, and BD is a tangent. Especially with tangents, I recommend that you highlight them. Now let's look at the solution. There we have our diagram, and we want to prove that ABD, there's ABD, it must be similar to BCD. Let's have it, there's BCD, right? So it's good to identify the two triangles. So those are the two triangles we need to focus on. Now we want to find our first angle. Remember I said that read your angles. That can give you a guide. ABD and BCD. So there's a D, and the D and the D is in the same position. Although there's a B and a B, the B's are not in the same position. A must be B, and that other angle B must be equal to C. So it's definitely the D and the D. So we'll start off there. So our first pair of angles is angle D, and we know it's the same D, so angle D is common. So there's our angle D. Angle D belongs to both. You can see that belongs to both. Second one, we need to get another angle, but we mustn't forget, you see that BD, what is that BD? That's correct, it's a tangent, right? And there we can use the tangent chord. You see the tangent chord theorem? That's correct. So our second pair then would be angle B1 equal to angle A. There's B1 and angle A. Do you see the tangent chord theorem? That's correct. So then you write down the reason, tan chord. Then we need to get our third angle, and we see our third angle is C. But don't write down C, it must be C1. And matching with, you see there's my other bigger triangle, ABD. So it's C1 with angle ABD. You can't write down angle B, it's wrong. You must write down the 3 letters there. ABD, not angle B, because it's the whole angle B there. Be careful about that, right? So it helps just to identify. You can see they identified the 2 triangles because the one triangle is inside the other one. And then your reason for the third one can just always be sum of the angles of a triangle. Then we can get our conclusion, and maybe you can just write it down in this order that they have there. ABD is similar to BCD, right? You don't have to go and check because you've proved the 3, so this definitely is similar to that. Rather write it down that way instead of making a mistake. So there I have ABD similar to BCD, and you write in here angle, 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 right? Now let's look at the application to the similarity part there. First part we prove the similarity, so let's see how we can apply that. There we have, we want to find the length of BD. So this is the length of the tangent that's unknown. So the CD is 8, so insert the 8 in the sketch. AC is 10, you insert that in your sketch there. Now, if you have proved similarity, you must use the similarity. If they are similar, that's right, the corresponding sides are in proportion. So there I've got my similar triangles. So I know AB with over BC and the BD over the CD and the AD over the BD. You should do that with your eyes closed actually. So there's our proportion. But we're not going to use all 3. Let's see what information is known and what is unknown. AB, no length. BC, no length. So I definitely am not going to use AB over BC. So I will have to use the other 2. So let's take the other 2 there. So identify the pair that you're going to use. BD in this case is in both fractions. So BD over CD, and CD is 8. So that's BD over 8. But AD is 10 plus 8. Right, so then we can cross multiply. BD squared is 8 times 18, so BD will be the square root of that, which in this case is exactly 12 centimeters. Let's look at example number 6. Here we're going to prove 2 triangles similar by using the concept of equiangular. So in this diagram here, it's important we always read there. We've got EDC is a tangent, right? So it's advisable here, let's highlight the tangent. There we got EDC as a tangent. Then another important thing is that AB is a diameter. AB is a diameter. So let's just highlight that so we don't forget that. And then EM is perpendicular to AB. Then we put that in. We've got D4 is X, and we see there's our X there. And now we have to prove 2 triangles similar, and then we have to make a deduction from that. So it's important here that you read your question. EDC is a tangent, so obviously you'll have to use a tangent, some tangent concepts there, tangent theorem. And there you got a circle, so you need to know your circle theorems as well. M is a center, so you know if that's a center. AM is a radius, MB is a radius, and MD is a radius. So you've got a number of radii there. And AB is a diameter, so there's a reason why this is a diameter, stated as a diameter. You can get something there. And EM is perpendicular, so we know that angle there has to be 90. On the next slide, we'll show you actually how to do the solution. But you have a chance here to also try it on your own. Now let us look at the solution to 6a. And 6a, we want to prove that triangle AMF. Right, let's see where's AMF. There's AMF, so it's that triangle there. And we want to prove that it's similar to ADP. So we know what to focus on. So there's AMF similar to ADP. Now, first of all, always remember that you must read your information, understand all the information. Like we had a tangent, so we can use our tangent theorem. There's a diameter, and that EM is perpendicular. So, which is the first pair? Again, here, maybe just look at the lettering. AMF and ADB. So that gives you an indication. Let's start with the A. So if I look at angle A, easy. Angle A is equal to A, right? Then the next angle there, let's see what information do we have there. You can see, look at your AMF, you can see there M3 is 90. That's in the little green triangle. M3 is 90 because it was given to us. Then we have to now look at the other one. I see ADB is also 90. Why is that 90? That's correct. That's why it was mentioned. Angle in a semicircle. AB is the diameter. Therefore, ADB is also 90. Angle in a semicircle. So there we've got our second pair of angles. The third one, you can just see there, we already have A and M3, so there we have F1, and the other one that's left is B2. So we can just write that down, and our reason why they are equal, that's correct. Always sum of the angles of a triangle. Now, therefore, we proved that triangle AMF is similar to triangle ADB, angle, angle, angle. Now let's look at the second part of the question 6b. There again we have our diagram, and this is what we have to prove. 2am squared equal to AD times AF. Now always we've just proved similarity. So from the similar triangles, what can we get? We can get the proportion. So let's get the proportion there. And the proportion from the similar triangles is AM over AD is equal to MF over DB is equal to AF over AB. Now, there we've got three fractions. We have to see which one is the one that we're actually going to need. And if you look at the question there, we need AM, so we definitely need to use the AM. Okay. AD, the question also wants AD. We don't want AF, we don't want DB, but we need AF. So it's the first fraction and the last fraction there. So identify that, because you can see from the question, I need an AM, I need an AD, I need an AF. The only thing that is not required in the statement that needs to be proved is AB. So in other words, we just have to replace AB. So AB needs to be replace. Now we look at our diagram and see with what can we replace. Let's see, there's AB, and what do we know about AB? AB is a diameter, and what do you know about the diameter? The diameter is double the radius, right? So it can be double what? It can be double AM, or it can be double MB. Let's see which one we need. We want AM, so I don't want to introduce another side in here, so I can, the AB is actually double the AM. So I'm going to actually replace AB with 2AM. We go back to the statement here again. So in place of AB, we replace AB now with 2AM. Now, let's just cross multiply. And if we cross multiply now, we notice we get 2AM squared equal to AD times AF. And what do you notice? There, this is the statement that we require to prove. 2AM squared equal to AD times AF, right? Let's just briefly go over that. Whenever you have similar triangles, you can get the proportion directly from that. Okay? And what we also have is that you have to now just out of the proportion, you see which pair is actually needed. Go to the question and you see what's there. And if you now have identified your pair, then you can just see which part of the proportion need to be replaced, because we want a AM and we want a but we don't want a AB. So AB needs to be replaced, and then we go to the diagram and see with what can we replace AB with. And that's how we proceed with this type of question. In this unit, which consists actually of 5 subunits, we're going to look at indirect applications, right? And we're starting off with the first one, which is the one where you have to prove that
the given proportion is valid. In other words, we first of all have to determine which two triangles are to be proved similar, and from the similarity we can then derive the required proportion. And that's what we're going to do in this section of the video. Now I want to share with you a strategy for solving indirect problems. Let's take the first type of problem here. We want to prove this proportion, right? Now, what is key to remember is that if triangles are similar, then it implies their corresponding sides are in proportion, right? So if I want to show that this corresponding sides are in proportion, I need to first of all show that the two triangles are similar. And when we have similar triangles, we also need to know that the order of the labeling of the triangle is essential. So I want to show you a strategy from the proportion that you want to prove, how we can identify the two triangles and at the same time write down the triangles in the correct order, right? So let's see. So our strategy here is to identify two triangles, but at the same time, the triangles labeling must be in the correct order. So let's take, there we've got a proportion, and what we know about a proportion, it's a ratio equal to a ratio. So let's take the first ratio, in this case we write it as AM over ME. And what I'm going to do here is I'm going to just color code it to make it easy. There's a and a M and a M and a E. What do we notice there? How many letters are there? Only three. A, a M, and a E. So from that we can identify three letters, right? And if I have three letters, they can form a triangle. There I have A, M, and E, and I've just color coded it the same way. So let's look at the numerator. There's the triangle. What's a triangle? A-M-E. There's a A-M-E. Only three letters. So if I look at the A-M, we see A-M is obviously opposite the E because there's only three letters, right? So if I have A-M, it's opposite angle E. And if I take M-E, what is the third letter? M-E, the third letter is A, right? So in other words, I already have identified the two letters, a E and a A. So what is the third letter? The third letter is obviously M because there are only three, a E, a A, and a M. So there I have the triangles now E, A, and M based on the fraction that I have there. You see A, M, E. So A, M, what's the third letter? E. M, E, what's the third letter? A. And E, A, what's the third letter? Third letter, we just fill it in. And exactly the same way, if I now take my other triangle, there's my ratio. BD is to DF. So what do we see there? A B, a D, and a F, three letters. So let's look at the numerator. BD, what's the third letter? The third letter is obviously a F. DF, what's the third letter? DF, it still needs a B. And there I have a FB, and what's the third letter? The third letter is a D, right? So in other words, the two triangles that I require to prove to be similar are actually EMA, and they've got them in the correct order there. F will have to be equal to E, and A will have to be equal to B, and M will be equal to T there, right? Let's just go over this again. First of all, I take the proportion. So I take the one fraction, and from that one fraction I can see there are three letters. And once you have the three letters, there's a M, and a E. AM, so the third letter must be E. ME, the third letter must be A. And if I have an E and an A, the third letter is obviously M. Similarly here, BD over DF, there's a B, a D, and an F. We're going to see something else as well. So BD, I need a F. DF, I need a B. And then I have a D. Now, what do we notice here? The letter that's repeated, you see there's M and M. That letter always comes in at the end. Okay? D and D always comes at the end. So I don't even have to look at the diagram. I can just look at the lettering of the proportion AM over ME, and that can give us our two. From the lettering, you can see what are the triangles, and then at the same time, you get them in the correct order there, right? Now we're going to practice this in the next slide for you to get used to the strategy. This is going to be the key strategy for solving indirect type of problems there. In other words, identifying the two triangles and at the same time, not just identifying them, having them in the correct order there. Let's get some practice. You have to try the following there. There are 4 proportions, and from each of these proportions there, you must get the similar triangles, and remember it has to be in the same order. I've color-coded it just to assist you there. Let's see, 1 minute should be more than enough. Okay, let's see now. There I have FRRE. So there's a F and an R and an E. So FR, I need an E. RE, I need an F. And the third letter has to be a R. Okay. GTM, so I need a M. And the TM needs a G. And then I need a T. Let's look at the next one. MTN. So MT is opposite N. NM is opposite T. And then the third letter is a M. GTE, so I need an E. ET is opposite G, and the third letter has to be a T. Okay, let's look at the next one. Here we see that we can't form them PT over ME, but I can take them horizontally. Okay, so there I have BTB, so opposite PTB. So opposite PT I have a B, opposite BT I have a P, and then the third letter is a T. MED, opposite ME, I need a D, and opposite DM, I need a E, and then I need a M, right? There again, I take RHB, so opposite RH, B, opposite BH, R, and then a H. DK, MD, so opposite DK is a M, opposite MD is a K, and then I'll need a letter D. So you can see you can do this very quickly. You just need to practice it, and you can master this quite easily. Now let's look at an example where you can apply the strategy here, and we're going to look at an example 7 where we're going to look at the type B1. So there we have a diagram. See the diagram there. AB is the diameter of a semicircle ADCB, and chords AC and BD. There's chords AC and BD, and they intersect at E, and EP is per. It's always important here that you read your information carefully. Diameter, and maybe what you can do is just highlight the diameter. A diameter tells me angle in a semicircle, that should be a 90. AB, that also tell me D, so the diameter is a clue there. As a semicircle, that I'll say angle in a semicircle. And we have EP, so there we have EP, that's 90. So I know if P1 is 90, obviously P2. So I have a lot of 90s in here. And here we have to prove, and you see there's a proportion that we want to prove. So it's important that you always read your information, highlight the given information, because if it's given that something is a diameter, you have to use it. If that's perpendicular, you need it as part of your solution. It will never be that you have a problem and something is mentioned, it's a diameter, and you don't need to use that diameter in your solution there. Now, you can try this on your own first, and then you can look at the solution in the next slide. So the solution, there we have our diagram again with all the information given, especially the important fact that AB is the diameter. And this is our question. We want to prove this proportion here. Now, always remember, if the triangles are similar, then the corresponding sides are in proportion. So if I want to prove this proportionality, I need to first of all show two triangles similar. So let's get our two triangles, right? So we have to get the two triangles in order, and we'll just use our strategy we did previously. There's BPPE, so there's 3 letters, a B, a P, and a E. So I start with E, then B, then P. Easy. Next one is a BD and a A. So I have BD, I start with an A, then I say A and a B and a D. Very quick, right? So let's identify there's the two triangles, EPB, and the other one there, the larger one there is ABD. Now we're ready to prove them similar. First pair, obviously you can see there, just looking at the labeling there, I have a EBP and I have the B and the B is common. We can even see from the two triangles there that we've identified with the dotted lines, B1 is common, right? So we start with P1 equal to B1 is our first pair. Second pair, now let's look at the one triangle. Let's see what's the given information. We need to get a second pair, and we see there that P1, how big is P1? P1 is 90, right? And we look at the other triangle. Do we see a 90 in the other triangle? Yes. ADB or angle D is also 90. Why? Angle in a semicircle. So let's identify that. So there we have our two pairs of angles equal. Third one, quite easy. There's the third angle there, and that is equal to E. Don't say E, it must be E3, and E3 is equal to not angle A but angle DAB. You can't say angle A, there are many angle A's there. Be specific. And now we can write down the similar triangles, and we got them in the right order. A B and a P and a E, and that was a B and a D and a A. Yeah. And once we have the similarity, remember similarity implies the corresponding sides. Now we can get the proportion. But we don't want all three. We have to see what is actually required there. We want a BP and a BD. There's a BP and a BD. We want a PE and an A. So it's the first two that I require. But we want it written in the required form. So I just have to interchange the BD and the PE. So interchange them, and there we've proved. Okay. And there the only thing that we had to do first here was to identify the two triangles, and there we identify them, and we also have identified them in the correct order. You can see E with A, and we did have E with A, B with B, and we got the B equal to the B, and angle P with angle D, we have angle P matching with angle D. So they are definitely similar. They are similar, they are corresponding sides are in proportion, and then we can identify the required proportion that we want there.
Now let's consider some the second type of indirect type of applications.
Now let's consider the second type. Here we have the second type here, and it's a proportion written in this form, AB, and then we have BF times MN over NT, right? Always remember that if triangles are similar, it implies the corresponding sides are proportion. So if you want to prove a proportion, we first need to prove the two triangles are similar. So how do we go about this one? Very simple. We just write it in our standard proportion form. And what do we mean by the standard proportion form? We want AB over. So I can bring over the BF. So it's AB over BF. Or I could even have brought over the MN. It doesn't matter. So just take any one of the numerator. So that becomes AB over BF. And there we have it in the standard form. And this standard form is actually our type B1. And we know what to do with that. Once we have that, we can write the triangles in the correct order. There's AB over BF and MN over NT. I've color-coded just to let us follow. So I have ABF. So quickly, ABF. So that's going to be FAB. Easy, FAB. There I have MNT. Very quick, MNT. So that's going to be TMN. N must come at the end. And now we're ready to do that. So what you do actually here, this type B2 is just one step different. You just write it in that form, and then you follow exactly the same procedure that we followed in P1. Now let's look at an example of the indirect type B2. This is example number 8. There we have in a diagram alongside, AB is a tangent to the circle with center O. There's circle center O. And BA is parallel to EC, and you can see there that this is what we want to prove. This is our type B question there, right? Always remember that you have to read your question carefully. So the key words there is tangent. So maybe highlight the tangent. That reminds you to apply the tangent theorem. It's also mentioned that BA is parallel to CE. Apart from the other fact here that we have a cyclic quad and we have angles, we have a lot of theorems with regard to circles that could possibly be applied. But the key ones here are the tangent and the parallel line. Okay. Now in the next slide we're going to actually look at the solution, but you can pause here, try it on your own, and then we can look at the solution then. Let's go to the solution. Now let's look at the solution. There we have our sketch with all the given information and the essential parts been highlighted. AB is a tangent and AB is parallel to EC. And this is our question. Always remember, if triangles are similar, it implies the corresponding sides are proportional, or the converse. Right? Now this is a B2, so we want to get it into this form. So how do we do that? AD, just put AC over AD, so there I've got it in the standard proportion form there. And what's our objective? We want to get two triangles in order. So let's just take the numerators. Let's look at ACCF. Let's focus there. I get a triangle ACF, and I get another triangle AD and a C. But we just want to get it in the correct order. So ACF, that means it's going to be FAC. And the other one is ADC, that's going to become CAD. There we got it in the correct order. Let's just identify our two triangles. That's FAC and the other one is CAD. So that's what we need to focus on. So let's start now with our first step. First pair, we can just look at the labeling here. FAC and CAD, there's an A and an A. So go for the A, right? So angle A, which angle A? We have to be specific. Angle A3 is common, not A, angle A3. Then we need to get a second pair. And there we can see there we have, so there the A3 is common, right? So let's look, get our second pair. And we use our given information. And here we're going to use a multi-step procedure here. So what do we have? We have C2. You see C2 is alternate to A4. We're using the parallel lines, right? So there's C2 and that is alternate to A4, right? What else do we know? What do you know about A4? A4 you can see is next to the tangent. So let's use the tangent theorem. So A4 is equal to angle D1, tangent chord theorem. So there we have two pairs of angles equal. Third pair, just easy. We can see there we still have to have angle F1 equal to angle ACD. And there the reason is sum of the angles of a triangle. Therefore, the two triangles are similar. So I have ACF similar to ADC, and that's angle, angle, angle. Once we have the similarity, we can get the proportion. First two over the first two, the last two over the last two, the first and the last over the first and the last. Easy. So let's get our proportion, and there we have our proportion there, right? But we need to identify which specific ones we want. We want the AC, so I definitely need the AC. There's an AD and a CF. So we can see in this case it's the first two. And now we just need to write it in the required form by transposing the AD to the right side. And that is AC equal to AD times CF over TC. And there we've proved it.
Now let's look at the third type of indirect type of applications.
Now let's look at the strategy to solve the third type of indirect problem. And this is the type here where we have the proportion, but it's written in this product form. AB times EF is equal to BC times DE, right? Always remember that similarity improves proportionality, right, of triangles there. So we have to now first of all take that expression there, and we want to write it in our standard form. Otherwise, I want AB over, so it's AB, I can bring in over the BC, and I just transpose the EF, or whichever. I can have AB and bring over the DE, then I just have to bring over the EF on the other side there again. So let's see there. And they have written in that form. You can double check. AB times EF is BC times DE. And once it's in this form, we just have to write it in the correct order. And by now you can do that with your eyes closed. So let's see there. AB over BC equal to DE over EF. So this is ABC. Let's take it this way. ABC. So that's going to be CAB. CAB. And there's DEF. So that's going to become FDE. Very easy. And then we're ready to prove that they are similar. Now let's just consider an example where you can apply the indirect type B3 problem. There we have a diagram. Let's just look at the diagram there. PQ is the diameter. PQ is the diameter of the circle. There we've got a circle PWRQ, which actually makes, right? SP is a tangent. SP is a tangent at point P. And we've got some straight lines. We've got QWT is a straight line, and QRS is also a straight line. And we've got angle P equal to X. And we have to prove this here, right? So this is the proportion written in this form. Always remember, read. So let's highlight and see the important. It's mentioned that's the diameter. Angle in a semicircle is going to be properly used there. And then we've got a tangent. We have to use our tangent theorem, either tangent chord theorem. And don't forget that diameter is also perpendicular to a tangent. So try to read and interpret your question so that the given information, so you understand diameter, it will have to be used. Tangent, you can use the tangent theorem or tangent concepts as well. You have a chance now to just try this question on your own first, and then in the next slide we'll show you the solution. Now let's look at example 7 and look at our approach and the full solution there. There we have our diagram, and let's just make sure we've got PQ as a diameter. So remember, angle in a semicircle, we've got the diameter and a tangent. So we need to remember the diameter is perpendicular to a tangent, and a tangent, we can even use the tangent chord theorem if it's necessary. And obviously there we have a triangle, and don't forget your triangle concepts as well. So this is the question that we have there. Always remember, we are busy with similarity, right? If triangles are similar, it implies the corresponding sides are proportional. So we want to prove some proportion here. So we need to first find out which triangles are similar, right? But we can write that expression in a standard form, okay? And what would the standard form be here? The standard form here would be, we take the ST and we bring the ST on the other side. ST we divide by ST. The QS we divide by QS. So there's the expression that you can just check there. If we multiply, we get exactly the same expression. Now, we want to get two triangles. And this is now easy for us. We've done this many times. We can either take the fraction there, we can take the numerator. Let's take the numerators one. QWR. Let's just check. QW, there is a triangle. QST, so it's definitely there are two triangles. But we want to get them in the right order. QWR, the W is repeated, the W will be the N, so the answer there is RQW. Similarly, we've got QST, the S is going to be at the end, so it's going to be TQS. You're used to that already. So there we've got RQW and TQS. Let's just check. There's RQW, let's just identify it, and there's the other triangle TQS. We immediately notice the one triangle fits in the other. Which one? Angle Q1 equal to Q is the same Q1. We can even see from the lettering there's a Q and there's a Q. So we already have our first step. Q1 equal to Q1 because they common. Okay. The second one here, we now need to find
you know, W must match with S, W with S, but that's not so obvious. Let's look at the other one. R must match with T. It's also not so obvious there, right? So here to get the second pair of angles, we'll have to follow a multi-step approach here. Let's look at what was given. We've got angle P1 is X, and P1 there is equal to which other angle do you see in that circle? That's correct, it's equal to W2. You see there's P1 and there's W2, angles in the same segment. Okay, so there we've got that X, and that other one is also going to be X. Now, what do we know about a diameter and a tangent? They're perpendicular, so we can work out P2. P2 is 90 minus X, right? Because the radius is perpendicular to a tangent. But PQ is a diameter, and when we have a diameter, we've got a right angle in a semicircle. Which angle is that? R1. So R1 is 90, therefore R3 will obviously be 90, angles on a straight line. So we've got R1 is 90. Now if we have a 90 and a 90 minus X, we can easily work out angle S. Angle S is just equal to X from either the sum of the angles of a triangle, or even using the exterior angle equal to the two opposite interior angles of a triangle. So there we've got two pairs of angles that match. The third pair, we can just fit in the third pair. The third pair would be T2 that matches with this WRQ. Please, you can't just say angle R, it's WRQ. I just follow the dotted. You can even see T2, there's only one, so that's T2. This one here, look at the yellow, it's WRQ, not angle R. And then we can write the triangles in the correct order. We know Q matches with Q, and W match with S, and R match with T. And once we have the similarity, what do we get next? That's correct, we get the proportion, right? And what would the proportion be? The first two over the first two, the last two over the last two, the first, that should be easy now. So there we get the proportions there. QW over QS, and WR over ST, and QR over QT. But this is not what we want. We want that expression. So we need a QW, so we definitely need the first fraction. ST, we need the second. So that's the pair that we will need. But we don't want it in that form, so we just multiply, cross multiply, and there we get our required expression. QW times ST, just follow, QS times WR. And there we've proved that. So what we've done actually here is we've just first of all transformed this into a standard form. And from there it's like a B1 type. Then we just have to prove the similarity using our standard procedure. First pair, second pair, and third pair. Just watch out, sometimes to get the second pair you need the multi-steps to be able to do that. You don't go directly from P1 from W2 to S. You don't go directly from W2 to S. You have to go, you see the W2 links with that one, and then that one can give me this one, and that one, you know, so it's quite a procedure. You don't go directly to that. You go via, right? It's not a straight route there. That's we follow a multi-step procedure there. Now let's look at the fourth type of indirect type applications. Now let's look at the strategy that we're going to follow for the type B4 problem here. And this is what we mean by B4. It's we have AB squared equal to a product, right? So it's a side that's squared equal to the product of two sides. Always remember, we're busy with similarity. And with similarity, if two triangles are similar, it implies that the corresponding sides are in proportion. Or if the corresponding sides of a triangle, two triangles are in proportion, it implies the triangles will be similar. So what we're going to do is to write that required expression in a standard form. AB squared is AB times AB. So I can bring one of the ABs over, and I can maybe bring the AC over. This is what we have. So I write it in the standard form. And you can see there, AB times AB is AB squared. AC times BS, so I can either bring over the AC or the BF, doesn't matter. Now we have to get the triangles in the correct order, and by now you know that very well already. I have A, B, C, so in other words the A is the same, so the A will be at the end, so that will just be CBA, easy. Okay, that's CBA. You can see there's BF AB, so there the B will be at the end, so it just be the FA, right? Very easy. You just have A, F, B. And now we're going to look at an example where we can apply this strategy. Now let's consider an example where we can apply type B4 type of example. There we have a diagram. HLKF is a cyclic quadrilateral, so we see the cyclic quadrilateral there. HFKL, so we have to know that we have to use cyclic quadrilateral theorem. Chords HL, there's chords HL and FK are produced to meet at M, and there we have KL parallel to. So the important thing is here we've got the parallel lines and we've got the cyclic quad, right? So that is what we're going to do. And here we have a type B4 where we have a square equal to a product. And in the next slide here, now let's look at the solution to example 10 following our strategy for that. Let's see, there's our diagram. We've got KL parallel to FG and we've got KLHF is a cyclic quadrilateral. And we have to prove this expression here. Now, if triangles are similar, their corresponding sides are in proportion, or the converse. Okay? So the first thing that we have to do is we want to write this required expression in a standard form. And that is the standard form. How did we get that? MF squared is MF times MF, so I can just divide by the 1 MFs and bring the other MG over. You can just confirm here. MF squared is MG times MH. Now it becomes standard now. We want to get the two triangles. Let's look at MFG. If I look at MFG, there's a triangle. MHF, MHF, so definitely those are two triangles that exist. MFG, the M is common, so the M will be at the end, so the answer is just GFM. The same way there we've got the M's common there, so the triangle will be FHM. Right, let's see GFM. Let's see where there's GFM. That's the larger one. FHM, that's the one that fits in it there. So we can already see it fits in, so we've already got our first pair of angles, angle M. And we can even see from the lettering here, there's a M and a M, so we start with M. Angle M is equal to angle M because it's common. Now we have to show that G is equal to F. G equal to F. That's not so obvious. Or we have to show that F is equal to the H. This angle F here is equal to this angle H. Not that obvious, right? So we're going to use a multi-step then. Let's use the given information. The lines are parallel. Look at the parallel lines. There's L1. And L1 will be equal to which angle? That's correct, equal to G, because the L1 is equal to G, the corresponding angles. The lines are parallel. Okay. Now, what else do we have? We have a cyclic quad, and L1 is the exterior angle of that cyclic quad. So L1 is equal to F2, and that's the exterior angle of the cyclic quad. There we got our two pairs. Now we just have to get our missing pair there. We can see here. So the missing pair there would be the MF with H and the MH with a F. It's this other angle there, that whole angle there, and this whole angle here. So I can just write them down. And that is because of some of the angles of a triangle. Now we can write down the triangles in correct order. GFM is equal to FHM. And from the similarity, we can write down the proportion. Write it down, should be very easy. GF over FH and GF over FH and FM over HM and GM over FM. But that's not what we want. We want to find MF squared. So I have to see there's a MF, and so this is the pair that we actually need there. And if we now multiply out and write it in the required form, Fm is the same as MF. So MF squared is Mg times MH, right? So what we've done there first, the only thing we've done differently from the previous is we've just wrote this required expression in the standard form. And then our question is again the standard way of solving the problem there. Now this brings us to the last type of indirect type of applications. Now let's consider the last type of indirect problem, P5, and this is the type of problem that we have here. If we notice there we've got squares and squares, but here we have, normally we multiply, here we've got addition involved here, right? So when we have squares together with addition, we can usually, that is an indication that we need to apply the theorem of Pythagoras. Look here, AB squared is BD squared plus another square, or we can sometimes even have subtraction there, right? So this is the indication that we will need Pythagoras to be able to solve this particular problem. And we're still going to use our proportion or similarity concept together with the theorem of Pythagoras. Now let's look at our last type of indirect question here, which is the indirect type B5. And example number 11. In this diagram alongside here, we've got LK is the diameter. So we see LK is the diameter, and we've got P is the center of with center P. P is the center of a circle. R and S, that's a tangent, and we also have that TP is perpendicular. So there's the given information. It's always important that you read your given information. LK is a diameter, so you should know that P is the center, so LP is equal to PK, and we also know that here that LNK, or in other words N2, will be 90-degree angle in a semicircle. There we've got our tangent theorem, so we can have the tangent chord theorem that we can apply here, right? And that perpendicular is what we're going to need. So there we have a level 1, a type B question, which is a direct question here, just proving them similar, and then we have this one following from that. Now let's look at the solution to example number 11. The first one here, as you can see, is a very direct question. They clearly ask you, prove that two triangles are similar. So we have to show K is equal to K, and T is equal to L, and P is equal to N. Very direct, very easy. So let's make sure we understand our diagram first. That's a tangent. We can use tangent concepts, and that's a diameter. We need to use the diameter concept. So let's see now. Let's identify the two triangles first. Okay, there's the one triangle and there's the other one. So you can see the one fits in the other. That you can immediately see angle K is the same. You can even see from the lettering there, K and K matches there. So the first pair of angles is angle K is equal to K, and that is common. The second pair here, now let's look at what information is given. It's mentioned there that TP is perpendicular, so angle TP, we can't get them in one step, so TPK is 90, that is given. And we also have L and K, that's on N2, that's also 90, and the reason for that is angle in a semicircle. Now we can see those two angles are equal. Very easy. So the third angle there would be T2 with L. So T2 matches with L, and that's the sum of the angles of a triangle. Therefore, triangle KTP is similar to KLN, and we just write down angle, angle, angle. And then we've proved that. Very easy. Now let's consider the second part of the question. This is what we need to prove, and we can see there we've got squares and we've got a subtraction there. Remember what we said, if there's subtraction or addition, we will most probably use the theorem of Pythagoras. So let's see now. In the previous question there, whenever you have similarity of two triangles give you the proportion of the corresponding sides. So we're going to write down the proportion, and the proportion from KTP being similar to KLN is KT over KL and TP over LN and KP over KN, right? Now we just need to see which pair do we need. We need a KT and a KN. So I need the KT and I need the KN. So those are the two pairs that we're going to need. I need the KT fraction with a KT in, and I need the fraction with a KN, right? We can then cross multiply them, and then we get that KT times KN and KL times KP. And we know KP is not, we don't want a KP, so we'll have to replace the KP. We don't have KL, so we have to replace it. Okay, so let's see. If we have to replace the KL, as you can see, KL is the diameter and P is the center. So KL is twice the radius, twice the KP. So we're going to replace the KL by twice KP. And 2 times KP is 2 KP squared, right? Now we want to replace the KP now. And if I look at KP is in a right angle triangle. So I can apply the theorem of Pythagoras there. So KP squared, using the theorem of Pythagoras, is KT squared minus PT squared. And now I can substitute the KP squared there, and KP squared. So instead of KP squared, I write down 2, and that's the expression. And if we look now, that's exactly what we want to prove. KT times KN, and 2 times KT squared minus TP squared. Right? You can see there, we use proportion together with the theorem of Pythagoras there. And that's the level 4 type of question, and it's not really that difficult. So you should just identify whenever you have questions like this and there's product and there's addition or subtraction and a square, most probably it's going to be the theorem of Pythagoras that needs to be applied there. Now we're ready for the exercise worksheet. I suggest you to go through the previous slides again. Look at a particular question, pause it and try it again there, right? And once you understand, then I suggest you start with the exercise worksheet, which consists of 5 questions actually taken from external examination question papers. This is a question adapted from February 2018. As you can see there, immediately there are 2 questions on similarity. This one again is a question adapted from the 2015 June examination question paper. And this is a November 2015 paper. This is a February 2016 paper. Question 5 is a question adapted from the February 2015 paper. When I write down adapted, sometimes I just change some of the wording, or maybe take out some questions, or maybe adapt the diagram slightly there. Thank you very much for viewing this video on similarity theorem, which is part 2 of a 2-part series. In part 1, if you haven't viewed it, there's a video on proportionality and the proportionality theorem and the converse of the proportionality theorem, as well as applications, right? You're also reminded to view other videos on this YouTube channel of ours, the Govan Mbeki Mathematics Development Centre, Nelson Mandela University YouTube channel. Please subscribe to our channel and watch all the other videos that's there. We trust then that you enjoyed this video, and then that you benefited from the video as well. Thank you very much.